I will refresh our memory about the integral test. That was what we spent most of our time last time talking about. I just have a couple of examples for you all to try, and then we'll go on to some other things to discuss. The integral test is about, so here's the idea. If the series, if some function f is decreasing, this only works for a decreasing function, then this, I didn't write it in this way last time, but I find this an easier way to remember it. Then the convergence of some f of n, so the series, is the same as the integral 1 to infinity f of x dx. All right. I say the convergence is the same. What I mean is if one of them converges, then the other converges. And if one of them diverges, then the other one diverges. So another way, to me, I find it easier to just remember, okay, if I want to know if this one converges or not, that's the same as if this one converges or not. That's what I mean when I say the convergence of this is the same as this. If you wanted to write in detail, I would say, i.e., if integral 1 to infinity f of x dx converges. Can you read what I'm writing here? Sorry if it's unclear. So does the sum f of n. N equals 1 to infinity. And if it diverges, then so does the other one, right? So the convergence or divergence of the series is the same as the convergence or divergence of the integral. And what's the point of that is that we have plenty of tricks for evaluating the integral. We do not have a lot of tricks for evaluating the series. So by transforming the series into the integral, that often makes it easier. Did everybody get the...
Two people still need that.
Yeah, I don't know if everybody's here, but... All right. I have some for you all to try. Sorry, I hope you don't mind just starting off trying some on your own. Let's try. So in each case, I'll give you two series. Say if they converge or not. Remember, the integral test only tells you whether or not it converges. It does not tell you what it actually converges to. So first one, the series e to the minus 3n, and the second one, the series n plus 1 over n to the 5. See what you think. The idea is you change it into that integral and then try to see if the integral converges or diverges. There's not paper at. Are you done? Anybody else need the paper? All right. Thinking about how to do the integral. Technically, they should be x's, not n's. It's now continuous. I would say try and simplify that fraction sometime. Doing okay?
Yeah. Does this look great for the?
Yes. So your answer is
Like the series conversion.
it converges. Yeah. That is not actually the answer.
Oh, okay.
It's the integral equals that, but the series doesn't equal that. It just means the series converges. Okay. Mm-hmm. I think so. Converges. Yeah. Okay. So that means that the integral equals that. So it converges, which means the series converges. So what happens when you make this infinite?
What? I think so. Wait.
I would say
Yeah. You don't think so? If you bring. If you. Yeah, you can change it to.
For the second you can just multiply out the, no, then you don't need to do yourself. You bring it apart and then you can just multiply it.
Oh.
Then you don't have to do yourself.
Oh, yeah, you're right.
I'm like, I think, like, I'm pretty sure that's correct.
Yeah, that makes sense.
I would suggest. You can actually simplify this. Nice way. Okay. Alright.
How do you do this one? How do you do this? What is this? Like, when you multiply it, it's like
It should be to the minus 3.
Oh. Oh, okay. Yeah.
Because of the negative exponent.
Oh, yeah, yeah. Well, yeah.
Yeah, they can just say,
Plus 1. So that's good. I'll give it another minute or two and then we'll talk about it.
When you say that, you're supposed to do
Yeah.
That's
Did you do this?
So this. This is not the same. I would say it's an opposite cancel, but it's a function. All right, let's chat about these. So the first one is fairly straightforward as far as these go. I make it a lim, t goes to infinity, integral 1 to t, e to the minus 3x dx. The integral of e to the minus 3x is 1 over minus 3, e to the minus 3x. And then I'm going to evaluate at 1 and t. I forgot my lim. Lim t goes to infinity. Right, like that. And then I plug them in. Lim t goes to infinity of minus 1/3 e to the minus 3t minus 1/3 e to the minus 3 times 1, right? And then you do this limit, and this part becomes 0 because it is a negative exponent there. So it's e to the negative 3 times t, and t is becoming infinite. Since it's a negative exponent, it really means I have e to the 3t in a denominator, and when that becomes infinite, it's an infinite in a denominator, which means the whole thing is 0. All right? It's because the exponent is a negative power. That becomes 0. This is what remains, and so this converges. The integral converges to this number, 1/3 e to the minus 3, I guess. And so that means the series e to the minus 3n converges. It does not necessarily converge to that same number. In fact, it almost surely does not converge to that same number, but it converges to something, which is all you can conclude using the integral test. Great. As I was walking around, can I say, I saw a lot of people at some point or another wrote a step involving this, or maybe even something like negative 1/3 e to the negative 3 infinity. This I consider to be bogus. You won't catch me writing something like that. Like, this is not I know what you mean when you write that, but really I would say, in public, in front of your parents, you kiss your parents with that mouth that writes e to the minus infinity. There is no such thing as e to the minus infinity. When you write this, I think what you mean actually is this. That's why we write it this way. I mean e to the minus 3t, where this t is becoming infinite. That makes sense. That means something to me. This is kind of bogus. I guess I know, I can guess what you mean when you write that. But I would say, in polite company, we're all friends here, so I know what you're talking about, but really, you shouldn't be writing something like this. When you're in the club, don't talk like that. In the DMs, they will not go for it if you write infinities like that. All right? Infinity is something which belongs in a limit. It does not belong plugged into an actual expression. Okay, great. Anyway, just real quick, let's do the other one. The other one is fairly similar. The only thing to really worry about is how are you supposed to do that integral, but hopefully as I was going around, people settled on it. So you change this into this integral, x plus 1 over x to the 5 dx, right? This, you do this lim thing, which is not a big deal. The real deal is, how do you do that integral? And in my opinion, the way to do this, there are a few different ways you could write this. Maybe this is the most straightforward. I will write it that way and then distribute the x to the minus 5 across the other part. So it becomes x to the minus 4 plus x to the minus 5. And now that is an easy integral to do, each one separately, right? You separately do them. It's going to be, I have a minus 4 power, I add 1, it becomes minus 3, so it's 1 over minus 3 x to the minus 3, and then similarly, plus 1 over minus 4 x to the minus 4, and then we plug in 1 and t. And again, since those exponents are negative, when I plug the t and make t go to infinity, those parts go to 0. So this eventually, well, I can't tell what eventually it becomes. It's a lim, t goes to infinity, 1 over minus 3 t to the minus 3 plus 1 over minus 4 t to the minus 4 minus 1 over minus 3 times 1 plus 1 over minus 4 times 1. Anyway, these two things both go to 0, and so it converges. The integral converges, which means the original series converges. So I hope that that's what you said. It is not really important what the answer of the integral is. It's just the fact that it converges. All right, great. This is, I think, all we need to say about the integral test. And I think we got plenty of time. We can talk about the next test. Like I said last time, we're going to talk about several different tests. One thing that I didn't really mention in these examples, I don't know if you were all thinking about this, but I will just remind us, the integral test only works if the function you're talking about is a decreasing function. So in really every time you use the integral test, you should first verify that that is a decreasing function. So the function in this case, e to the minus 3x, the graph of that looks like this, and that is decreasing. And so it is allowed to use the integral test on that one. Yeah.
You also take the derivative and if it's negative.
Yeah, I think generally speaking, the easiest way would be to look at a graph. But yeah, if you wanted to do it sort of by hand without using a graphing computer or something, you could take the derivative and show that that is always negative. Yes, although that is often kind of hard to do. Although in this case it wouldn't be, because the derivative is negative 3 e to the minus 3n, which is negative because of the negative 3. Yeah, this one, that would be a bit harder, I think. This one also, though, when you graph it, it looks vaguely like that. I mean, this one has a vertical asymptote at 0, so it looks something like that. But anyway, it's decreasing. All right, great. So that is the major limitation of the integral test, right? This is why, like, what's the point of having more tests if we can already use the integral test? The answer is the integral test only works in this particular situation when the function is decreasing, which is not always the case. What we have next is something called the comparison test. This one is actually a very simple idea. It's just saying something like, if you have a bigger series and a smaller series, and you know the bigger one converges, then automatically the smaller one also converges. The idea is, if we have something like, smaller, less than bigger, and you know the bigger does not go to infinity, that means the smaller also does not go to infinity, because it's impossible for a smaller thing to go to infinity if the bigger thing does not go to infinity, right? This is the basic idea. If the bigger thing is always bigger than the smaller thing, then the convergence of one depends on the other. That is to say, if the bigger converges, the smaller must converge. And also, if the smaller diverges, the bigger must diverge. That is, if the smaller one is going to infinity, then automatically the other one is going to infinity. So that's what the comparison test is all about. It's based on taking a complicated series and comparing it with a simpler one that you already, for some reason, know how to deal with. So I'm going to write this in more formal terms, but it's all just based on, if we have smaller, less than bigger, can I just say the convergence? Convergences are related in that slightly complicated way that I just said. That is to say, if the bigger one converges, the smaller one also converges, and if the smaller one diverges, the bigger one also diverges. Anyway, I'm going to write this all out formally speaking. So generally, we're talking about two serieses, and I'm going to write them as one I'll call AN, and the other one I'll call BN. And the idea is, if you have some way of comparing the two, then the convergence of one of them is related to the convergence of the other one. Okay, so here's what it is. I'll write this as a theorem. This is called the comparison test. I'll write it out formally, and then we'll do a bunch of examples. The comparison test. Okay, one very important thing about this, so this also has sort of limited applicability. This one only works if, I'm going to say let AN and BN be positive for all n, all right? They need to be positive for this whole reasoning to work, because you don't want a situation where one is going to plus infinity and the other is going to minus infinity or something like that, all right? Like what I just said about smaller and bigger, I said if the bigger converges, the smaller must also converge. That's because I know the smaller is not going to negative infinity if the bigger one is going to some positive number. Anyway, they have to be positive. There are variations of this which work, for instance, if they're both negative, but we don't need to get into that. Variations. Positive for all n. Okay, then, here's the real deal. There are two versions. If the bigger one converges, then the smaller one also converges. So that says, if the sum of the Bn converges, and the A's are smaller than the B's, then the sum of the A's converges. All right? So this says if the bigger one converges, then the smaller one also automatically converges. And we can say a similar thing about diverges. So the second one is about diverging. It says if the sum diverges, if it diverges and it's the smaller one, so and bn is less than or equal to an, then the sum of the an diverges. This can be a little confusing to keep straight sometimes, unfortunately. You have to be careful about which one is the bigger one and which one is the smaller one. And the way that our book writes it, they like to use the less than or equal to sign both times. And so here, in the first case, the b's are the bigger one. In the second case, the b's are the smaller one. This is how our book writes it, which might be a little confusing, I don't know. But anyway, the first one says if the bigger one converges, then the smaller one converges. And the second one says if the smaller diverges, then the bigger also diverges. All right? This is called, these are two different things, I suppose, but this is called the comparison test. All right? And the typical way that we do this is, I will say you use it by compare a weird sequence, or series is what I should say. Compare a weird series with one that we already know. And the ones that we already know are the geometric series, which I will just write once again. This is geometric. The sum a r to the n minus 1, and this one converges when, and remember the rule about when this converges? You should remember this eventually. When absolute value r is less than 1, yes. And the other series that we are often going to compare with, we had the geometric and we also had the harmonic, but actually the harmonic is a special case of what we call a p series, and that is the sum 1 over n to the power p. And this one we talked about just at the very end last time. This one converges when p is greater than 1. When p is less than 1, it diverges. I should say for both of these. Diverges otherwise. Can I squeeze that in above? Diverges otherwise. All right. The geometric series and the p series. Basically, you should have those two kind of types of series memorized together with the specific condition about when they converge and when they don't. All right. That p series we just talked about at the very end last time. All right. So let's try some examples. I got a few. I got some for you, although I don't know if we'll get that far. But how about the sum? I'm going to say 2 over n cubed plus 3n plus 7. All right. Your job is say whether or not it converges. Or if you're lucky, I will tell you and then say something like, show that it converges. So this one actually, I happen to know ahead of time, this one does converge. So let's show it converges. All right. How are we going to show it converges? I'm going to use the comparison test, of course, because that's what we're talking about here. By comparison with, so you always compare the series you're given with one of the sort of stock series that we already know about, which are, we basically just have two choices at this point. If, in the future, if we learn about more types of series, that's more options for comparisons. But you should try to compare it somehow with something that looks similar. So I would say, looking at this, does this look more like a p series or more like a geometric? Anybody have an opinion about that? Yeah?
Looks more like P series.
Looks more like the p. Why do you say that?
Because it has like an n to the something power, which has the P series?
Yes, n to the, rather than to the n. That's really the big difference between these two things. When you see n inside an exponent, generally speaking, that's going to be something like a geometric. When you see a power of n, I expect that to look like a P series. All right, so I'm going to show this by comparison with the P series. That's because what I see in there is powers of n, not n inside powers, or n inside the exponent. If you see n inside the exponent, you should probably view it as a geometric. If you see a power of n, then that's probably more appropriate to compare with the P series. All right, so that means I want to show it converges. Now the P series also converges. So in terms of the biggers versus smallers, I want to show that this is the smaller. This is smaller than something else which converges. So in order to set this up right, I'm going to show this by comparing with the P series. We need our series to be smaller than a P series which converges. That's the idea. If you want to show that your series converges, you have to show that it's smaller than something else which converges. And if you want to show that yours diverges, you have to show that it's bigger than something else which diverges. All right? We need our series to be smaller than a P series which converges. And here, unfortunately, or maybe fortunately, you have to have some amount of creativity because there are many ways that you could make this work. But what you have to do is look at this thing. I want to say, basically, my terms that I'm looking at here are 2, sorry, I scrolled it, n cubed plus 3n plus 7, right? And I want to say that this is less than or equal to, smaller than a P series. So what I put over here, don't write this down exactly, but something like, 1 over some power of n or something. Anybody have a suggestion? What should the power of n look like? I know we've never done this before, but yeah?
3 or greater?
3 or greater. I'm going to actually use 3. Actually, this is a little counterintuitive, but you should not use 4 here because 1 over n to the 4 is actually smaller than 1 over n to the cubed because the denominator is bigger, which makes the fraction smaller. If you want it to be actually this to be bigger than that, you should use the same power or maybe even a lesser power, right? Is that actually true, this inequality? I mean, I just wrote that, but you have to think, this can be a little taxing, but you have to think hard about the numerators and the denominators here, right? When I go from here to here, I made the denominator smaller, right? The denominator here is less than this because they match the n cubed. The only difference is this one has a little bit of extra stuff, right? So actually, this side, the denominator is smaller. So that means this side is bigger, right? Is this actually just straight up true then? We should also consider the numerators. Now the numerators, we have a bit of a problem. This is not greater than 2, right? 2 is greater than that. So instead, we will do one very simple modification, and that is, I'm just going to say 2 over n cubed, all right? And that really is true. So if you, you don't have to justify this every time you're doing one of these, but this is true because I made the denominator smaller, so the fraction is bigger. I'm not sure if you're used to thinking in this way. I find these kind of arguments to be very confusing, and I have to stop everything else in my head and think carefully about the denominator getting bigger, which means the whole thing gets smaller. It can be a little confusing. Hopefully we all get used to it. All right? And now 2 over n cubed. This, of course, is the same as 2 times 1 over n cubed, and that part converges. This is the whole idea. Right? That extra 2 doesn't really matter because you can always factor a 2 out of a series. All right? So anyway, this is sort of my kind of scratch work or something. This is my basic idea, but to tie it all together and really make the argument formally speaking, I'll say something like we have if I start with this series, 2 over n cubed plus 3n plus 7, this is less than or equal to this series 2 over n cubed, which is 2, the sum 1 over n cubed, and that converges. That converges because, remember, the p series converges whenever p is greater than 1, and here it's 3. So this converges since 3 is greater than 1. And so, by the comparison test, our original series also converges. N cubed plus 3n plus 7 converges. All right. And again, there's no need or there's no use even to say what it converges to. You can't say what it converges to. All you know is that it's less than something else which converges. This doesn't actually tell you what the thing you started with converges to. Just only that it does converge. All right. Let's try another one. So you have to get used to kind of looking at these things and figuring out what am I supposed to be comparing this with. Let's just try some examples. I got 2 more, and then I have some for you. Maybe 2 more might do us. We'll see. This is a strange series here. Sine squared of n over 2 to the n. Sine squared of n over 2 to the n. So should I be comparing this with a geometric or a p series? Remember, the difference is geometric has n in the exponent. The p series has n to some power. I would say this one has n in the exponent. Now I also have sine. I don't know what to do with that, but for the sake of this n in the exponent down here, I'm going to compare this with a geometric. And you also have to decide for yourself, do you think this is going to converge or diverge? It matters because that will determine if you want to think of this as the smaller thing or think of this as the bigger thing. Anyone have a feeling for this? Do you think it's going to converge or diverge? When you add this up, does it become like infinite or add up to something specific? The only thing that I would compare this with would be this. I would say it looks like 1 over 2 to the n, right? And that one, we talked about this. This one actually adds up to 2, right? This is, that's a geometric series. You can work that out. The difference, though, is this sine squared of n. How are these fractions related? They're almost the same, right? One is less than the other. My comparison is going to be like this. What goes in the middle? I'm either going to write a less than sign or a greater than sign. The denominators are the same, so really it's just a matter of the numerators. Is 1 bigger than sine squared, or is sine squared bigger than 1? I think 1 is bigger. Just sine by itself is between -1 and 1, and if you square that, it's going to be positive, but it's still between 0 and 1, right? Yeah, question?
Can you explain why we're using geometric series to compare?
So it's because when I look at this, it looks like I have n inside the exponent, which is what geometric series looks like, versus the other one, the p series, has some power of n, which I don't see at all here. Now there's also this sine thing, which is weird, but as far as what is immediately recognizable in here, I see n in the exponent, which makes me think geometric. So I think they said this, less than or equal. And that really is just straight up less than or equal. You don't have to do any kind of factoring out a constant or anything. And the reason this is because since sine squared of n is always less than or equal to 1. It really is. Because ordinary just sine by itself would be between -1 and 1. And then when you square that, it is now still in that range, but has to be positive. So it's between 0 and 1. All right? So what does it look like when we tie all of this together? That means the sum sine squared of n over 2 to the n will be less than or equal to the sum 1 over 2 to the n. And that converges because that's a geometric. Now, as far as the geometric, you have to say what is the r being in the correct little range here? Can anybody say what's the r in this one? If you're not sure, you can just work out, the terms here. A1 is 1 over 2. A2 is 1 over 2 squared, right? And then you do the r thing is by dividing A2 divided by A1. It's 1/4 divided by 1/2. That is a half. You may have to do a little figuring. But anyway, this r being less than 1 in absolute value, that means it converges. And so that means by our comparison thing, it means what I started with, not n squared, 2 to the n, converges. Right? All right, let's do one that diverges, and then maybe I'll have you guys try one that diverges. I think we got enough time for that. All of these have been converging, and that's why in all of these examples I was using the less than, because when you want to show that something converges, you show that it's less than another thing which converges. For diverging, you want the other way around. To show something diverges, you want to show that it's bigger than something else which you know diverges. So let's try the sum cosine squared n plus 1 over n. All right. Now this one I would like to compare with p series. So I see n down there. If your choices are geometric or p series, geometric is when n is inside of an exponent, which I don't see that here. I do see, I suppose, a power of n in the denominator. It's n to the power 1, right? So this I am going to think of as a p series with p equals 1. So I compare that, cosine squared n plus 1 over n, versus just straight up 1 over n. And which way should the inequality sign go this time? I think this is a greater than. The denominators are the same, so we don't need to worry about the denominators. The numerator on the left is 1 plus something, so it's a little bit bigger than 1. So this goes that way. And so that means my sum here, cosine squared n plus 1 over n, is greater than or equal to just the series 1 over n. And that series is a p series with p equal 1. So it diverges. And so what I started with is bigger than a diverges, which means what I started with also diverges. So what I started with also diverges. Cosine squared n plus 1 over n diverges. Because it's bigger than another one which diverges. Right. These are a little tricky in my opinion, just because this inequality step, it's not always obvious what you're supposed to be saying here. But hopefully they will work out. I got one for you to try. We got a few minutes here. I don't know if there's enough time to finish it entirely, but let's show that, how about 1 plus natural log of n over n. Is that confusing? ln n? This series diverges. This is actually very similar to the one we just did. We'll do maybe some more interesting ones next time. Everybody's doing great. Can I make it a little more interesting? Well, let's do it this way, and then I'm gonna try and make it ever so slightly more interesting. This one, so you can basically follow exactly the steps from the previous example. You compare this to 1 over n, hoping that the natural log doesn't really matter, and the comparison should go that way, because on the left what I see is 1 plus a little something extra, but that's more than just 1, right? So the comparison looks like that. But the one on the right, we know this is going to diverge when we put it in a series. So it'll say 1 plus ln n over n. The series is greater than or equal to the series 1 over n, and this diverges, right? That's what I saw everybody say. How about this? Can we make a little cute variation? What if I put a 3 there? You can do almost exactly the same steps, but anybody have a suggestion? Let's just try and write, the next step would be 3 plus ln of n, just copying exactly what we did there. Greater than or equal to what? What should I put on the right there? Yeah? 3 over n. Yeah, I like that. Yeah, so now when I try and write out that last step there, I would say sum 3 plus ln of n over n is greater than or equal to sum 3 over n. And now what? Now I know that 1 over n diverges. What can I do with 3 over n? Yeah?
Pull the 3.
Yeah, pull the 3, he says. Pull the 3 out of the sum. Yeah, great. So sometimes you have to do extra, cute little tricks. This diverges, which means 3 times that diverges, right? And the rest of the proof works the same way. Yes?
Why did you have to make it 3 over n? Could it just be 1 over n?
Oh yeah, I like what he's saying. Isn't that still greater than 1 over n? The answer is yes, it is. You could have just put 1 over n, because 3 plus natural log of n is actually just straight up bigger than 1 over n. Yeah. Yes, you are more clever than me. Yeah. Great.